So last time we had given one step towards the proof of this theorem. Today I'll actually start with an idea of the proof that will tell you why we needed that particular lemma. Okay, and then we'll go ahead with the proof. Now, how does one prove this thing? So it is proved using the help of this power series or generating function, okay, for the sequences PIIN and FIIN essentially. Now we already know that PIIS into 1 minus FIIS is equal to 1. This is 1 for all s in minus 1 to 1. If you write both PIIS and FIIS completely, this is what the identity would look like. Now let's go formally without giving justifications. If you do that by taking limits as s approaches 1, okay, what we get is that this sum of the PIINs times 1 minus sum of the FIINs is equal to 1. Okay, and hence 1 minus FII, which is 1 minus FIIN, this sum is essentially 1 over the sum of the n-step transition probabilities of returning to I starting from I. Okay, and of course then what follows is that if this sum is infinite, then this is 1 over infinity, so 0, therefore FII equal to 1. And we already have discussed this last time. FII equal to 1 just means I is recurrent. On the other hand, if this is finite, then this would be something positive, and therefore FII 1 over this would be something positive, and therefore FII is strictly less than 1, which will show that I is transient. Okay, so this is the idea of the proof. This is the argument essentially. But of course, this is not completely rigorous because there are some issues here. We are taking this, first of all, this equation only valid in the open interval minus 1 to 1 in general. And then we are taking the limit as s approaches 1 from the left side. Question is, why would the limit exist? And even if it exists, why will it be equal to the thing that we want it to be? Okay, for both of these quantities. That's the first thing. Secondly, we are also writing this as 1 over this, even in the case when this is infinite. What does it mean? So how are we going to handle the case when this sum is actually infinite? Okay, so not only when this is finite, suppose this is infinite, will this still converge, or rather will this still diverge to infinity as s goes to 1 from the left side? So this question also has to be answered. So all of these has to be justified, and then only the proof would be complete. So the proof, which looks longer than just this one slide, is just making all this rigorous. And in order to make this rigorous, we actually need this result, Abel's limit theorem, which we stated last time. And this is precisely about this kind of limits that we need. Okay, so suppose you have a power series which has a radius of convergence which is strictly positive and finite as well. Let's call it R. Now define a function through this power series in the interval, open interval minus R to R. Now the question is whether this can be extended to the closed interval, say minus R to R. So Abel's limit theorem states that if this is summable at s equal to R, if this power series is summable at s equal to R, then the limit of AS will exist as s approaches R from the left side, and this limit actually would equal to this sum. So in particular, this means that this function defined by this 1, this can be extended to this semi-open interval minus R to R. which is closed on the R side. Okay. Similarly, you can have a statement about minus R. I'm not writing it because we are not going to need it. And then that will tell you whether it can be extended, this function can be extended to entire closed interval minus R to R or not in a continuous way. So this is not only an extension, it's also extension in a continuous way. Okay. Now on the other hand, if all the terms of the sequence are non-negative, and you know that this series is not summable at s equal to R, so it diverges, then still this will hold, except that this will be infinity. So still as s approaches from left side to R, this limit will be infinity. So this as will also diverge at R. So both of these statements are going to be useful for us. And in the last class, we had given the proof of the lemma, which used the first part of Abel's limit theorem. Today, we are going to use both the parts. Okay. What is the first step towards the proof? We had this lemma last time. This says that for all I in S, the limit of FIIS exists as S approaches 1 from the left side, and this limit equals the probability of starting from I, the Markov chain comes back to I in finite number of steps. Okay. Now, how did we prove it? Let's go over the proof once more. So there are two cases. If the radius of convergence of the power series, this power series, this is the generating function corresponding to the sequence FIIN. If this radius of convergence is strictly bigger than 1, then FIIS, which is given by this power series, is well defined and continuous on the entire open interval minus Ri to plus Ri, which contains the closed interval minus 1 to 1. And therefore, this defines a function, continuous function on the closed interval minus 1 to 1. And therefore, trivially, this limit is equal to FII1. In fact, you don't have to approach from the left side. Both limits are actually equal, and it equals with the value of the function at 1 because it's continuous at 1. And then this FII1 is just the sum of the FIINs, which is, we remember, this is just, by definition, this is just sum of that starting from I will come back to I exactly after n steps for the first time, and which is giving you the probability that, this is finite starting, the tau I1 is finite starting from I. On the other hand, if the radius of convergence equals 1, then since this sum is finite, so this sequence is summable, we'll be able to use Abel's limit theorem, the first part, which will tell you that FIIS, even though it's not, it's a power series on the open interval minus 1 to 1 only, but you can take the limit as s goes to 1 from the left side, and this limit will equal this sum, which is finite, and which actually is equal to this probability. So therefore, the lemma will hold in either case. So either it will hold because the power series has radius of convergence is strictly bigger than 1, in which case it holds trivially. If not, you just invoke Abel's limit theorem at the point 1. Okay? If Ri is equal to 1. So radius of convergence is bigger than or equal to 1. This is known. So in particular, if radius of convergence is infinite, then also this proof is valid, and we'll just have to use the first part. Okay, so this proves the lemma, and as I said, the lemma is proved with the help of the first part of Abel's limit.